Okay, my friends, sorry about that little delay. This will be our lecture for 11/6/2025, so this Thursday. I hope everybody's doing well. Too bad I can't be there tonight. I was looking forward to those presentations, but we will do that next week. So we don't have too much left to do this semester. So we'll have class next week. We'll have those final three presentations. And then we'll have a little bit of lecture next week. And then the following week, we'll have our second exam and our last in-class exam. And then we'll have the final after that. I think we'll be okay. I have to figure out how we're going to test on these presentations, but I think it's going to be doable. So we're going to have presentations, some tests on the presentations, as well as some of the material that we've talked about. And I'll have a little bit of a study guide or something to help us through that, maybe even make a little video like this. But I wanted to have a lecture for today. Let's talk about, this can be a review somewhat of what we did last week, but that'd be good for us. And then wanted to add a little bit of more material about what these fatty acids actually do structurally in the body and where they're attached to. So our free fatty acids, I would call them, that are just lone fatty acids, they are in the body for sure. But most of the fatty acids are tied up into more complex lipids that I want to talk about. So let's just review some of our fatty acids for a few moments. Okay, fatty acids are these simple organic molecules, and they are the building blocks, and they are the main active components generally, not always, of more complex lipids. So lipids that are found in fats, that are found in oils, and so these are found all throughout the body, and they're found in our blood. They're found in every single cell. So lipids in the form of fatty acids are just found all over the place. Each fatty acid has sort of two parts, as we discussed. The first part is the fat portion. I would call this the fat portion. That is these carbons bound to these hydrogens. Okay, this is fat. When we say fat, generally we would define fat as something that is not soluble in water. It separates from water. This is the fat portion, these long chain carbons. In this case, there are 12 carbons here. Okay, and this is the fat portion. The acid portion, this is what we would call a carboxylic acid in organic chemistry, but is composed of this C double bonded to an O and then OH. This hydrogen right here that I'm circling, this would be the acidic part. This hydrogen can actually come off much more easily, way more easily than these other hydrogens bound to those carbons. Because of the electronic structure of this carboxylic acid, then it's this hydrogen that I'm circling again that can actually be removed more easily from this fatty acid. And because of that, then there are some charges associated with that. And this truly is an acid. Okay, so this is a fatty, as I'm circling here, acid. And this has 12 carbons, and attached to each of those carbons in the fatty portion are hydrogens. These are very nonpolar, we would say that. And this comprises the fat. This is the acid portion right here. Now, it's annoying writing all of those carbons, those C's, and those hydrogens. And so a lot of times we will actually write this exact same fatty acid. This is lauric acid here. This is lauric acid over here. There are 12 carbons. Each vertice is a carbon, and it is implied that there are two hydrogens attached to each of these carbons. Okay, there is a hydrogen attached, and if there are no double bonds, it'll be two hydrogens attached. This is lauric acid, and this is lauric acid. Okay, this is the fatty, the hydrocarbon chain portion right here. Okay, this does not like water. It will not dissolve in water at all. And this is the fat portion. This is the acidic portion. It actually loves water. We call molecules like this amphipathic. You don't have to know that word, but that's what we call this. This is a fatty acid. These are hugely important in the body. Very, very important. We've been talking about that all semester. Okay, what are the roles of fatty acids? Fatty acids are used heavily to store energy. Very much so. Those fatty acids can be used in the heart, they're used a lot. They're used in muscle tissues, particularly when the sugars run out. And when sugars run out, there is no more sugar left to burn for energy. Then we will start oxidizing. We will break down those fatty acids to release energy. And there is a ton of energy. These are great for storage. We can store these energy in our fat cells. And so we talked about this last week, that in a famine, for example, the body breaks into those fat stores to get energy, to burn energy. When there is an excess, particularly of carbohydrates, of sugars, then our body says, I might need these fats later, so I'm going to store fats in adipose tissue. I'm going to store them in our gut, in our butts. I'm going to store them wherever I store fat because I might need them later. And this is the best way for the body to store energy, is in a fatty acid. Okay, so that's one thing that fatty acids are used for, energy storage. They are also used as structural components, particularly in membranes. Here's an example of a membrane that we talked about. These two leg portions of each of these molecules are the fatty acids. This is a cartoon depiction of those. And these orient themselves to the other fat portions of the same types of molecules, and we form what we call a bilayer. Here's one layer, here's the second layer, and these are composed of fats, fatty acids. The fats align with each other, and the water-loving portion, represented by those red circles, they align too, forming membranes. This is one of the great, great, great steps in evolution, that when we could spontaneously form these membranes, creating cells. That's what our cells are made of. This was one of the great movements, one of the steps forward to higher organisms, is the ability to form cells based upon these membranes. We've talked about this. A lot of people show these particular cartoons in their presentations. And this is very simple, but a cell membrane, here's also the exact same type of cell membrane cartoon that is far more realistic. It is a very complex structure with proteins in there, different types of fats in there. It allows for the movement of molecules, the controlled movement of molecules in and out. You want to control what goes into and out of the cell. And the ability of these fatty acids to form these bilayers is extremely important. What are the primary roles of fatty acids? Energy storage, structural membranes, forming membranes. These are the biggest roles of fatty acids. There are others. Fatty acids, for example, can function as messengers. They can be signaling molecules. There's other roles for fatty acids, but these are the two major ones. Now, we've talked about saturated and unsaturated fatty acids. A saturated fatty acid is where the fat portion, the hydrocarbon chain, has only single bonds. It is saturated with hydrogen atoms. Every single carbon has two hydrogens attached to it, except for the omega, as we've talked about, the terminal, that will have three. Okay, these chains are typically straight. They pack together tightly. If you remember, we talked about, for example, lung surfactant. That has a lot of saturated fatty acids because they can pack together tightly, forming this soap on the inside of our lungs that allows us to reduce the surface tension. Because those cells compact, those chains compact tightly together. Butter has a lot of saturated fatty acid. That's why it's solid at room temperature. Okay, things that have a lot of saturated fatty acids in them are solid because those chains compact so nicely together, and it takes more energy, more heat to break those down. You know, we can throw butter in the microwave for our microwave popcorn and it will definitely melt, but it takes energy to melt those. Unsaturated fatty acids are hydrocarbons that contain one or more double bonds between those carbon atoms. We've talked about that. This forms kinks. It bends the hydrocarbon chain, making them much harder to pack together tightly. And so that's why a lot of these oils, typically oils that we have at room temperature, are liquids. Okay, they have olive oil has a lot of 18-1, one double bond, as well as a lot of 18-2, two double bonds. Those are the two. Unsaturated fatty acids have double bonds in the hydrocarbon chain. Saturated fatty acids don't. They're saturated with hydrogen atoms. Not all in an unsaturated fatty acid, not all of the carbons have hydrogens attached to them. Okay, now if there are multiple double bonds, we call that polyunsaturated. Okay, it's just something that we use in our language as chemists. Okay, polyunsaturated. If it is monounsaturated, it only has one double bond. The biggest one probably being oleic acid, 18-1. That's the biggest one that's found in olive oil. I expect you to know these fatty acids. The 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to memorize 9 fatty acids. What am I asking you to memorize? I want you to know these 3 saturated fatty acids. If you remember our nomenclature, when I say fatty acid 12:0, we would just say 12:0. That means it has 12 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I got all of them there. Okay. Then this has 12. Fatty acid 12:0 is lauric acid. I want you to know the common name. Okay. 12:0 is lauric acid. You'll find this in shampoos and soaps. Very, very common. You'll find it moderately in the body. We don't have a ton of lauric acid. We do have some, but we don't have a ton in the body. It gets metabolized very, very quickly. You'll find it in coconut oil. It has a lot of this saturated 12:0, which means coconut oil, if you get some, it's a solid at room temperature because it has a lot of saturated fatty acids, in this case smaller chain fatty acids. Okay, so I want you to know that. I want you to know this guy is has the most of any in the whole body. Okay, fatty acid 16:0, which we call palmitic acid. It is saturated. Again, it has 16 carbons, 0 double bonds. Palmitic acid, found everywhere. There is not as much, but still some, stearic acid, 18:0, 18 carbons, 0 double bonds. These 3 saturated fatty acids I want you to know. Now let's just look at some of these unsaturated ones. I only have one monounsaturated. This is oleic acid that you can see here. It does have one double bond. Okay, this is oleic acid. It is likely an omega 9. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. It is omega 9. Not all 18-1 is omega 9, but most of it is. And you can see it forms a kink. It does form a kink. You can't pack these together too tightly. This is oleic acid. I expect you to know that. If you go, those 18 carbons, one double bond. If you go up, one more double bond, 18-2, linoleic acid. Linoleic acid. I think it is important to know that this is an omega 6. 1, 2, 3, 4, 5, 6. Almost all 18-2 is omega 6. The reason why that's important is that this will lead to downstream products that are pro-inflammatory. Oh my gosh, you don't want omega 6s in the body. You just don't want them. Okay, so this is 18-2, linoleic acid, 18-2. This is very, very common, extremely common. This is one that can be found in a lot of plant seed oils as well. Linoleic acid. Okay, so oleic acid, linoleic acid. 18-3 is called linolenic acid. All right, you can see a common frame there that makes it easier to memorize, probably. 18-3 linolenic acid. This is found in flaxseed oils. Okay, it is an omega 3. 1, 2, 3. Supposedly omega 3s are good for us. I suppose they probably are in limited quantities. This comes from flaxseed oil. If I take too much of this, it does something to my heart, makes it go faster. So it's probably not all good. Okay, 3 more that I want us to remember. Let's go to 24. This is the big guy. This is one. I'm going to move him a little bit. This is a big guy. This is maybe the most important fatty acid in the body. This is pro-inflammatory. It's an omega 6. 1, 2, 3, 4, 5, 6. Omega 6. Arachidonic acid, AA, arachidonic acid. This is very pro-inflammatory. When you take ibuprofen, something like that, this is its target. It blocks the conversion of arachidonic acid into further downstream pro-inflammatory molecules. This is very important to know. Fatty acid 24, 20 carbons, 4 double bonds. And the last 2 are our 2 fish oil omega 3s, EPA and DHA. EPA is 25. It's an omega 3, 1, 2, 3, as is DHA, 1, 2, 3. These are supposedly good for the brain. Okay, these are actually anti-inflammatory, we would say. The downstream products form what we call resolvins. It resolves inflammation. They're not as abundant as arachidonic acid. Okay, and so these are our polyunsaturated that I really want you to know. I want you to know EPA, DHA, AA, arachidonic acid, and oleic, linoleic, and linolenic acid. Okay, in terms of abundance, I don't expect you to know this, but we have, as I said, a ton palmitic acid. We have a ton of oleic acid. We have a ton of linoleic acid. These are the 3 big guys. These are found almost in all types of fats. Yes, you will find these others. They are there, but they're just not there in abundance. Okay, last time we talked about cis, and I drew these on the board, so it's hard to draw those here, so I'm not going to do that. But we will go to the next figure, and I think it'll show this. Okay, a cis fatty acid is a fatty acid where the hydrogen atoms are on the same side of a double bond. Cis and trans are only applicable when you see a double bond. Okay, this is what nature wants, a cis double bond. This is what our enzymes are evolved with, are cis fatty acids. This is the natural shape. This is what's found in oils and foods that are natural. It needs that kink. one of the problems supposedly, and I actually agree with this, are trans fatty acids. That is where the hydrogen atoms next to a double bond are on the opposite sides. What that does is it gets rid of the kink. It makes it straight chained like a saturated fatty acid. Okay, these are created through the hydrogenation, adding hydrogens partially to these fatty acids. We do that to increase the shelf life of these things. I think this is a big deal health-wise. I don't think it's a small deal. So let's look and see what it actually means. Okay, here is a cis fatty acid. Okay, this is that oleic acid. It's 18-1. And you can see the hydrogens are on the double bond. That forces that carbon chain now to go down and elongate here. That hydrogen on this, hydrogen is terminal. It will never elongate. The carbons just keep going. And in this case, that cis bend puts that kink in there. If it is trans, where it's on the opposite side, that allows that carbon to keep going in the same direction. You could not draw that on a cis. Cis, good, trans, bad. And I'm, of course, talking about fatty acids. Okay, there are two major sources. We didn't talk about this last week, but where do our fatty acids come from? Well, they come mainly from diet. Okay, 60 to 80%. That's a lot, but it's not complete. 60 to 80%. It depends so much. What do you eat? What's the diet? This really does depend, but anywhere from 60 to 80% of our fatty acids come from diet. Okay, there are certain fatty acids that we call essential that the body cannot synthesize. They cannot. We have to get these from our food. For example, linoleic, 18-2, but there's so much all around. That's not a problem. But linolenic acid from flaxseed oil, we do need to get that from our food. And so if we're not getting good sources of that, we're not getting enough linolenic acid. If you remember, 18-3. Most of our dietary fat is stored in the form of triglycerides, and we'll talk about those later. Okay, they are from triglyceride. This is where most of the dietary fat comes from. We take it in as triglycerides. Yes, we do take it in as other things, but mostly triglycerides. Okay, so the dietary intake of what we bring into our body influences our lipids so much. I've done some analysis where I have a colleague who eats a lot of fish. You can see so much more of those omega-3s in all of her lipids, not just her triglycerides, but in all of her lipids. So diet matters a ton. The second source of fatty acids is synthesis. We synthesize it de novo. We make lipids. Usually 10% to 40%, but this can vary. And this is, I think, a huge deal. Yes, diet is important. Okay, but our diet, if we take in too many carbohydrates, instead of taking that in from the diet, then carbohydrates is a source. It is a precursor molecule, or it makes a precursor molecule to start lipogenesis. So when we take in carbohydrates, candy has no fat in it. But if you eat a lot of candy, you are going to get fat. Why? Well, because it brings in the precursor to fatty acid synthesis. That's one thing. And if you do take in too much sugar, the body says, oh my gosh, I'm going to have to start storing all these fats that I'm making. And it stores them as triglycerides in our fat tissue. Okay, so carbohydrate intake really influences fatty acid composition in our body, which is a big deal. The end product almost of all fatty acid synthesis is 16-0, palmitic acid, which can then be converted into other things. We can make it longer. We can desaturate it, that is, throw some double bonds in there. But this is the end main product is 16-0. Okay, so diet is a big deal for two reasons. Number one, if it brings in our fats, that's one reason. But it also matters if we bring in too much sugar, because that is a huge source of fatty acids. Okay, we talked about essential fatty acids. These are fatty acids that our body can't make, so we have to get them. Okay, so a bunch of these are those omega-3s. Okay, this is alpha-linolenic acid, 18-3, 25, and 22-6. These are found in our fish oils, as I said, our flaxseed oils for the alpha-linolenic acid. These are good for brains, they're good for membranes. They lead to resolvins, which reduce inflammation, so we get them there. Okay, these are all omega-3s, but it's also important that we balance these. Okay, so with our oleic, our linoleic, and our palmitic acids. We need to really pay attention to what we bring into the body. And for maximum health, then we do need to at least have a source of our omega-3s. And I think this is well enough established to be the case. Okay, I want to talk about lipids. This is newer material for us. So we talked about fatty acids, but fatty acids in their free form, not attached to anything else, are in the body, but most of the fatty acids are bound. They're linked to other things. So let's look at these. I hope you can see certain themes or motifs here. Here is, for example, triglycerides. There's 3 fatty acids here. 1, 2, 3. These are triglycerides. Half or so, just going off of my analysis, of our fatty acids are tied up into triglycerides. Why? Because they have 3 fatty acids. It is triglycerides that are stored in our fat tissues mainly. Okay, so you can see fatty acids. You can see attached to cholesterol. This is the cholesterol portion, but cholesterol has the ability to esterify or bond. Okay, we bond one fatty acid to cholesterol ester. You can see the reason we call it an ester is this in organic chemistry. I'm not expecting you to know this, is an ester bond. But I hope you can see that there's one fatty acid attached to cholesterol ester. And in fact, the single lipid that is most abundant in the body would be a cholesterol ester that has 18-2 or linoleic acid attached to it. Okay, so cholesterol esters are important. When we speak of cholesterol, then we're actually talking about cholesterol itself plus cholesterol esters. And in fact, the majority of the cholesterol in our body has a fatty acid attached to about 70% or so. Okay, so here's a triglyceride with 3 fatty acids. A cholesterol ester has 1 fatty acid. And we have what we call phospholipids. When we're talking about membranes, we're talking about phospholipids. A phospholipid has, again, you can see these fatty acids attached. In this case, PC, phosphatidylcholine, has 2 fatty acids, along with this phosphate group here, phospho. You can see the P there. This phospho group right here. This happens to be something called phosphocholine. Okay, but a phospholipid has 2 fatty acids attached to a phosphate group. I hope you can see that. I hope you can be able to point out that this is a phospholipid. Okay, snake venom, when it comes into the body, actually comes in. How does it work? Most snake venom works by attacking these phospholipids and cutting one of these off. Boy, you could see the mess that would make in a membrane, maybe. And that results in what we call a lysophosphatidylcholine. One of those fatty acids has been cut off. Notice the phosphocholine, the phosphate group, is the same. The only difference between a PC and an LPC is that one of the fatty acids has been cut off. A very natural process that happens, but if you get snake venom in you, then that does a number on our phospholipids. And you can see there's other phospholipids where this head group changes a little bit. This is the last one I would expect you to kind of remember, is this phosphatidylethanolamine. The difference, and we'll show this a little bit later, is right here in that phosphate head group. Okay, so three major phospholipids, three major lipids I really want us to be familiar with. One is a triglyceride, which has 3 fatty acids. The second is a cholesterol ester, which has 1 fatty acid. And then phospholipids, which generally have 2 fatty acids. These 3, and these actually, I'm 5, are these 3, PC, cholesterol ester, and triglycerides, contains the majority of our fatty acids. Okay, I want to introduce to you a molecule that we call glycerol. Glycerol. The glycerol means it's an alcohol. This is an alcohol. This is glycerol. You can see that glycerol actually has 3 OH groups, 3 alcohol groups. An alcohol forms an OH. 1, 2, 3. This is the backbone for so many lipids. Okay? Why? Because you can almost look at those OHs as attachment points for fatty acids. That's what these are. This is where you snap those fatty acids on. For example, let's look at triglycerides. Okay, I already said they have 3 fatty acids. Can you see that right here is glycerol? This would be 1, 2, 3 alcohol groups, but chemistry has happened, attaching 3 fatty acids. You can see glycerol, a triglyc, 3 fatty acids attached to that glycerol. We have a lot of triglycerides in the body. Now you can see, I would say that we have about 20 to 25 different types of fatty acids that can attach to anything. For example, this looks like 16-0 to me. I'm not going to count. Let's just say it is. This top one is 16-0. This middle one looks like 18-1. And the bottom one to me looks like 18-3. I'm just going to say that that's the case. If you count and get it something different than then that's fine. Okay, so you can see a triglyceride can have so many different fatty acids. And in fact, when I do triglyceride analysis in my real job, I'm looking for roughly 400 different triglycerides that have different fatty acids attached to them. That's just the number of permutations that we can do. Okay, so a triglyceride, 3 fatty acids attached to that glycerol. Okay, I hope you can see that. Next, let's look at that. Let's make this bigger. Here is the, kind of stretches it ugly, but that's okay. Here is phosphatidylcholine. This also has glycerol, a little bit harder to see, but here's a carbon number 1 for glycerol. There's that O. Here's carbon number 2, which has that O. And here's carbon number 3, which has that O. In this case, 2 fatty acids have been attached to glycerol. But on the other end, instead of a fatty acids, we have this phosphate group. Phosphate is that PO4 right there. Okay, I just want you to be able to look at that, and I want you to be able to tell me, oh yeah, that's a phospholipid, Dr. Reese. And not only that, this happens to be phosphatidylcholine. Why? I'm only gonna have you distinguish 2, so it's not a big deal, because it has this nitrogen with 1, 2, 3 additional carbons attached to it. Okay, this is a choline group. This is a phosphocholene group. And the whole thing is called phosphatidylcholine, a phosphate. We'll learn about the importance of those in just a second. Okay, here is the second one. These are the only 2 I want you to know. Phosphatidylethynolamine. Well, what's the difference? Well, it still has the 2 fatty acids. Here's the glycerol, 1, 2, 3 carbons with those oxygens. Still has the phosphate group, and the only difference is that at the end has this amine group. It'll be an NH2, but if we add a hydrogen, it's an NH3+. But it doesn't have 1, 2, 3 more carbons attached to it. It's a little bit smaller. So if we go up, here's the choline that has 1, 2, 3 additional carbons. But down here, it doesn't have 3 additional carbons. It's a little bit smaller. This is phosphatidylethynolamine, PE. We would abbreviate that PE. PCPE. Okay, just one more here. Cholesterol ester. Here's the cholesterol molecule. So beautiful. It's so beautiful. It's such a beautiful molecule. It's not as dangerous as you might think it is. After this class, you know it's not. But notice how cholesterol, it's all is an alcohol, like glycerol, cholesterol. You can see that OH group right here. That OH group right there. Well, it turns out that in our body, we often attach a fatty acid to that OH group. And it can be any of a number of fatty acids. And this forms a cholesterol ester. Here is that ester bond, which I don't expect you to know. Just know that cholesterol can bond 1 fatty acid at that alcohol spot. Okay, we have a ton of cholesterol ester in our body. All right, just 4 more slides that I can see. 4 more slides. All right, let's talk about triglycerides. Why do we have triglycerides? Well, we have triglycerides because this is how we store the energy. If you were to get a big hunk of my fat cells, you would find so many triglycerides there. It is just a dense way to store all that energy. Okay, so this is energy storage. This is where we store the energy, is in triglycerides. Okay, and so when we eat, a whole bunch of hormones and enzymes come to deal with all these triglycerides. It's actually really cool. I study some of those enzymes. Okay, so the major function of triglycerides is for energy storage, and when the time comes to release that energy. Okay, the second is vitamins. Okay, these are what a lot of our vitamins are fat soluble. They don't dissolve in water so well. And so it's important that we have enough triglyceride to dissolve those vitamins that are fat soluble. Not all are, but many are very, very fat soluble. Vitamin D, vitamin E, these are fat soluble. Okay, so vitamins, energy storage vitamins, to make us warm. Okay, they're insulators, number one. That's their insulators. But we can also break down these fats to release heat. We call this thermogenesis, which is not in these slides, but that's what triglycerides are for. I got to sneeze here, my friends. Okay, that's another thing. Just to give us a little padding, give us a little cushion when we bump into things. Okay, they give us just some nice padding. And, my son was such a good swimmer, and he raced against this kid who was fat when he was younger, and the fat kid beat him, which was crazy. It shocked us all. Why was he fast? Well, he was good. That's one thing, but he had so much fat. He was buoyant. Some of the fast tech suits of long ago, where all these world records were set, was because it made people more buoyant and they're able to swim through the water better. Well, a lot of animals, including ourselves, fat is lighter than water. It floats to the top, and so fat can add buoyancy. Okay, these triglycerides can add buoyancy. All right, those are triglycerides. Energy storage, that's the number one big one I really want you to know. But also for vitamin absorption, for insulation, for padding, and to make us float. All right, PCs. Just remember PC. PCs, the number one thing are these membranes. Oh my gosh, this is by far the most abundant phospholipid in cell membranes for sure. Okay, so they do provide some fluidity, especially because they can dissolve other things. And I want you to remember that these membranes are so complex. They are so complex, these bilayer membranes. This is the major function of PC, is to form those membranes. Okay, now they're also used for other things like phosphatidylcholine. It uses choline to provide these neurotransmitters, acetylcholine. Okay, it's important for learning, memory, and they're crucial for our brains, and particularly our neurotransmitters. But not just our neurotransmitters; they also form the vesicles, the membranes for these vesicles, these small things that contain our small sacs, let's say, that contain our neurotransmitters. I mean, PC is so crucial. And yes, they function in cellular repair. I'm not going to worry about that too much. This last one, drug delivery, is interesting only in the fact that I analyzed in my lab some of the vaccines that were used for COVID, or COVID vaccines, these mRNA vaccines. Well, those mRNA vaccines have to be delivered by fat globules that the mRNA is dissolved into, and those fat globules are made up heavily of PC. So I could detect these PCs so we can use these for drug delivery. Phosphatidylethylamine, PE, doesn't have those 3 carbons attached there. I just want you to know just really one major thing is that they're used to curve the membrane. Remember I said that this group right up here is much smaller? Well, when you start to pack these things together, then these brown or whatever, these brown ones are the PEs, phosphatidylethanolamines, and because that top portion is smaller and narrow, it leads to curvature of membranes. So important. Isn't it crazy? It's so crazy how nature works. I just think it's so beautiful and crazy, and who would think of this? The God of evolution would think of this. But you can see that these lead to curvature. The PCs are mostly straight guys. Okay, the blues are the PCs, and they're the straight guys. But these phosphatidylethylamines add curvature to a membrane. And of course some fluidity and also some neurotransmitter issues. And then our last slide of the lecture is cholesterol. Why do we have cholesterol esters? Well, again, it stores cholesterol. When we say it's toxic, I have toxic here. What I mean by that is that cholesterol can dissolve into these plasma membranes, completely changing the fluidity. Very much so. And so you can imagine that if you have too much cholesterol, then that can lead to a breakdown of membranes. Now, cholesterol is so important for membranes, but too much is not. And so the way we can control that is we can say, well, I'm just going to throw a big old long fatty acid in there. And then that doesn't go into membranes very easily at all, a little bit, but not so easily in large part because this is so non-polar. Oh my gosh, these are so non-polar. So it modifies, it stores cholesterol, just changes cholesterol from being toxic to being non-toxic. And so these are moved throughout the body into what we call lipoproteins. The two you've heard about are LDL, the bad cholesterol, and HDL, the good cholesterol. I don't totally subscribe to those, but I know why. But these are transport. Cholesterol esters is a way of transporting cholesterol throughout the body, which is cool. Again, it stores cholesterol, makes it so it's not so active. And then when we need it, we can take an enzyme, cleave that off. We can make hormones. Testosterone we can make. A lot of different ones. Cortisol we can make. Okay, we can make these steroid hormones. And as I said, they can help in membrane integrity too. Okay, this is a lecture. Okay, and I expect you to know somewhat. Maybe on our quiz we can use these notes a little bit. I'll have to think about that. I want you to study this. I want you to know this. This will be kind of our second to last lecture. But this is good. Maybe I wish I would have recorded all these this way and then talked about it in class too, because this way we can store it for the future. But anyway, fatty acids are so important. I think our last lecture, we're going to focus on, well, when fatty acids go a little bit crazy, or how, because these are so important for the brain, and cholesterol is so important for the brain, then how can we have more healthy brains through diet, through fasting as well, that can make us stronger and better. I think this is so crucial, and I think, by the way, that our major health problem, let's say, in my opinion, particularly of the brain, comes from a imbalance, if you will, or I'll say imbalance of these cholesterol esters, not of neurotransmitters. I don't think that in large part are neurotransmitter modifying medications like antidepressants and such. I really don't think they're doing what we think that they're doing. But I think we can have a far more potent effect in our body. They say, for example, when you start taking an antidepressant for OCD, you need to wait 2 months before you really start seeing any benefit from it. You might start seeing it earlier, but that's what they say. 6 to 8 weeks, somewhere in there, is when you should start noticing things. Well, that bothers me for a lot of reasons. But how about just 6 to 8 weeks of diet modification, of maybe some intermittent fasting in there? I think you're going to see far more benefit than you will from taking those damn antidepressants. Okay, here's our lecture. Again, wish I could be there. Hope you guys are well. I'm going to try to put this up on YouTube. Not guaranteeing I can do it. Thanks, guys. See you next week. Bye.